So there's a number of extensions apart from the GRU and the LSTM that we've looked at, where you can extend RNNs even further. Okay, so you can extend basic RNNs in this way, but you can also extend LSTMs and GRUs in this way. And the one thing that's used very often is bidirectional RNNs. So in all of the examples that I looked at, we basically ran the RNN in the forward direction. But in some applications, you would also be able to run the RNN in the reverse direction. And then what you would get is you would get this thing called a bidirectional RNN, where you have basically two hidden cells, the forward hidden cells and the backward hidden cells, which are often denoted with the forward arrow or the backward arrow. And then your hidden state would be just the concatenation of these two. You stack them on top of each other. There's one little bit of danger that happens with a bidirectional RNN. And that is that you need to ask yourself, how am I going to use this thing at test time? So let me just give you an example. If we're doing next word prediction, so we're trying to predict the next word in a sentence, basically language modeling. Then when we're training our model, we've got our full sentences, right? And we can output something at every time step, okay, while we're training it. But you can't use a bidirectional RNN in that case, because what's going to happen is at test time, I won't actually have the next word that occurs in the sentence. The problem is you need the full, like at training time, you've got this full sequence running in this direction. You've got the full sequence. Okay, let me make it slightly concrete. We started with this language modeling example right at the start. And what this model does is it tries to predict the next word in the sequence. Okay, so if you're at time step 6 and the sequence is a long time ago and you're trying to predict the next word, then you get this distribution over the next word. Now, when you're training the model, you actually know that the next word is galaxy. Okay, and you use that to calculate the loss and backprop it. So you would train this thing on full sentences, but then when you're actually using it to predict, you've trained the model, you've delivered the model to your client, and the client is WhatsApp, and they're using it to predict the next word based on what I've typed before. Then you've actually only seen up to this point, and you ask WhatsApp, this person has typed a long time ago, predict the next word for me, and you need to do that without having seen the next word, okay? But when you're doing bidirectional RNNs, in this case, you will actually cheat. So let me just show you how that would happen. So let's say, I'm just going to simplify here, we have a long time, okay, and this is my like x1, and this is my x2, and this is my x3, this is x4, and this is x5, right? So, okay, and then let's say at this time step we're predicting a little distribution over the next word, okay? And at training time, what we're going to try and do is we're going to, from this vector, remember this is a big vector, and you're selecting at training time the element in this vector that corresponds to the next word, okay, which in this case is long, okay. And in the loss function, what I'm going to do is I'm going to strip out from this vector the probability setting at the word long, and that's what I'm going to use to basically optimize this model. Are you all with me? Now, if you're doing that and that's your task, you've actually cheated. Why? Because when I ran, the forward pass is fine. I take get the hidden representation and I stack that part there. But in the backward pass, what I've done is I've actually, in the backward pass, when I reach this word here, and I calculated this state here, the word long has actually influenced that hidden representation here, which means that that hidden representation has influenced that one there, which means that in that part, the word long has actually had an effect. And in effect, what you can then do is the model can cheat during training, and it would know where to look in this vector and where to put large probabilities, because you've actually told it in the backward pass what is coming into the future. You can sometimes do this, right? But not for language modeling, not for next word prediction, okay? You can sometimes use it in other cases. So let me give you one case, and that actually links with the next set of videos on encoder-decoder models, okay? So where could you actually use a bidirectional RNN is when I'm trying to translate from one language into another, okay? Because what happens now is if I type a sentence into Google Translate in Afrikaans and I ask it produce the English sentence for me, then Google Translate already has the entire sentence. It has the first word and it has the last word, and it knows where I've stopped the sentence. And it can use that in order to encode that model. And it can run a forward direct parse and a backward RNN in that case, and get a very good latent representation. But note, Google Translate can't use that to produce the English sentence, okay? Because in the decoder, you won't know at test time which word is coming next, because the decoder outputs one word at a time. You need to go through the encoder-decoder lectures to understand that. But here, you would then be constrained to use a forward RNN again. Okay, does that make sense? Okay, so sometimes you talk about a causal model. A causal model is one where you can only go forward in time. Like, we live in a causal world. We can't look into the future and then affect things. The other thing you can do as an extension of RNNs is you can stack them on top of each other. You can stack a bunch of GRU layers, or you can stack a bunch of LSTM layers, or a bunch of vanilla RNN layers on top of each other, where each preceding layer serves as the input to the next layer. And this people very often do. So if you read in a paper, we use 3 LSTM layers with this many hidden units per layer, then you know there are 3 LSTM layers and each has 100 units in a layer, for instance. The final thing I want to say about RNNs is that I haven't covered everything, okay? There's still more to read. And one thing in particular that I would actually encourage you to read is Andrei Karpathy's blog called The Unreasonable Effectiveness of Recurrent Neural Networks. That talks about more or less vanilla RNNs, okay? And then for LSTMs and GRUs, go and read Kola's blog, okay? Andrei Karpathy's blog is very, very nice. And in particular, one thing that I haven't really spoken about is this idea that sometimes you have an RNN that just has a single input and then produces a sequence of outputs, so that's that one-to-many. Sometimes you read in a whole sequence and you just produce one output vector right at the end. That's a many-to-one. You also have many-to-many in different varieties. But if you understand the basic building blocks of RNNs that we covered in this little lecture series, then you would be able to very, very quickly see how all of that maps to different types of structures like these ones. And then going into encoder-decoder models, which also follows a particular structure, you will actually be able to understand exactly what goes on there. Okay.